All right, folks, welcome to the world of Haskell. Haskell is a functional language, which means that much like mathematics, it focuses on functions and the evaluation of expressions. So you can make statements that might evaluate to something, like mathematical expressions. There are no changes to values. Expressions simply result in a new value. Much like in mathematics, you say x plus 3, and that doesn't change x. That creates a new value that you can reference that is whatever x was, and 3 more added to it. This also means that functions have no side effects. You don't call a function and it changes the list that it was called with or anything like that. Again, it might return you a new list that's based on the list that you passed in as a parameter, but it will have no side effects on the list that you gave it or the integer that you gave it or anything like that. There are no true uses of assignments, though we'll see that you can name values and use them as variables, but there are no assignments in the sense of x equals 3 and later x equals 7 within the same namespace or things like that. You can do composition of functions instead of sequences of instructions. So rather than thinking about this happens, then a separate other thing happens, we think about one function can be done to generate a new result, and the result of that is passed as the input to another function, and the result of that is passed as the input to another function, and so on until we get the final result that we wanted. There will be lots of recursive functions, and we can use these instead of our loops that we would typically use in a more iterative kind of programming setting. And there will be heavy use of lists and even other data structures, but they will be data structures that, again, are not mutable. They're data structures that we use and we use or get a new value from, or we build from, or that kind of thing, instead of, say, arrays where we can assign to each individual index. These will be lists that are built or that are constructed, and then we can construct new lists from them or construct results from them. It's worth noting that some other functional languages do break these rules. They do have assignments where we can keep a reference to something, much like a reference in Java or C++, and we can change that reference at later points. Haskell does not have that. It is a purely functional language. Similarly, some functional languages will have a semicolon operator so that you can make sort of iterative statements, x equals 3, semicolon, print x, these sorts of things. Again, a purely functional language like Haskell will not have these. And some functional languages have while loops or arrays that you can assign to. So again, you can get some more of that iterative style, that reference-based style that you might be used to. Haskell will not allow you any of these. It will purely be building new values from old ones, composing functions, meaning calling functions on the result of another function or combining their behavior in certain ways. And we'll see lots and lots of examples of those as we work through different Haskell stuff. Haskell is, however, a strongly typed language, much like some of the other languages you might have worked in, like C, C++, Java. Haskell is a strongly typed language. It does it in a way that will seem weird and unfamiliar at first, but everything is a value, meaning again that there are no variables which you can assign and reassign and change. There are only named values. So there is some value, and we may call it X for now. There is some value of a list that exists, and we may call it L or that kind of thing. Even functions and procedures that you type in are values. They're all treated as just values. You can even assign a function to multiple names, similar to variables. Every value then has a type. The type checking is done at compile time. What we're going to see when we get into deeper examples is that quite often the type checking is inferred from how you used that name or that value or how you did things inside of that function, which is what I think most students find the most difficult about most functional languages, is that you don't say int x typically. You sometimes can specify the type up front, but typically you don't specify the type. You just say x plus 3, and the system knows what types are allowed to have plus 3 done with them, and it will infer the type for x based on that. There are therefore no runtime type errors possible, unlike, say, class cast exceptions in Java or type errors in Python where you try to do something with the wrong type of data. You will never get to that place, which means that functional code like Haskell code can be very, very difficult to get through the compile step and get your code to actually properly match the types and compile. But once you have done that, you can rely very heavily on the types being correct. So that's one aspect of the program that you really never have to worry about in terms of the type of the data being malformed somehow or incorrect or mismatched or that kind of thing. There will be no casting or any of that. Types in Haskell are polymorphic, meaning that there are categories of types that we can use. So, for example, there is the general type that is often referred to by the system as A. This is not a real type. It's just a category of type that really is sort of a wild card and says it could be any type. So if I just state that I'm going to have some value that's named, it will probably be treated as A, any type. We don't know what it is right now. And so if you write a function that operates on type A, that means that that function can operate on any type of data. You can sort of think of this as being like object in Java, but not quite, not exactly the same. There's not quite inheritance in quite the same way, but you can sort of think of it as that sort of wild card that everything could be assigned to or could belong to or could deal with. And from there, we can narrow it down. So there are some other categories that things might apply to, and if you use those categories, then Haskell will refer to them in these sorts of ways. So if I check equality, if I check if my value equals another value, then all Haskell can guarantee is that my code is working on values that have equality measurements between them. And so it will say, we're working with some equality type. I'm not sure exactly what type it is, so I still use A, but I know it's an A that can have equality checked. Or if I do some mathematical operations with it, then often we'll be looking at a numerical type A. It still could be any of the numerical types. We similarly, if we have something that could be a value or could be this special value nothing, that's sort of like null, then we call that a maybe. And so it's treated as a maybe A. And we could even have an optional number, that it could be some number or it could be nothing. And then, as I mentioned before, functions are values as well. And so functions have their own types. Much like your functions in other languages have types, these are just written a little differently. So this would be the type of a function that goes from type A to type A, meaning its input is type A and its output is type A. And then here's another function that has two different types. Sometimes when we have more than one type, the Haskell system will use T and T1 and T2 to indicate those different types. So here we have something that goes from one type as input to another type as output. Since these are unconstrained, they're not number A or equality A or anything like that, then this is any type here, and this is the same type as output, whereas this is any type here and any other type as output, or any type at all. And so here's one that takes a string as input and gives an integer as output. It's worth noting that strings in Haskell are equivalent to lists of characters, but both names will work. So this takes a string as input and an integer as output, and it's some function. It's the type of some function. It's not itself an actual function, but it's a type. Here is a list that could contain any type as its item type. This is getting more complicated down here. Here's a function's type that goes from any type to unit, which is no output, sort of like void. Here is a function that takes two argument types, but in Haskell, this is shown as a function that gives a function that, so a function that takes any type and gives a function that takes an integer that then gives a string. So if you write a function with multiple parameters, it will be shown as a function that returns another function type. And we'll get into the details of why on this a little bit later, but just be aware that functions will look like they are returning functions of a different type, and they kind of are. And then here's a function that takes a pretty complex input type and comes out with a list of one of those any types inside of there. So it takes a pair, that's what the parentheses indicate, is a pair or a tuple, that first has a function that goes from T to T1 types, and the second part of that pair is a T, and it's going to accept a whole list of these tuples and come out with some single result. This is a pretty complicated one, but it shows you some of the range of the different types that can exist in Haskell, and that some of them belong to sort of this very broad any category, like my A's, my T's, my T1s, etc. And some of them belong to a little more constrained of categories. And there are even very specific categories like int or string as well. So I mentioned that these types are learned by Haskell through inference. So here's an example where I wrote a function called f that takes x and y. You'll notice this is different notation than you're probably used to for a lot of other languages, but you state that it's f, and then the following things are its variables. It takes x and it takes y. It returns x minus y. It results in x minus y. You can query the type of things in Haskell by using :type and then the thing you want to check the type of. I believe you can shortcut this to :t as well, and then the name of the thing you want to check the type of. So here it tells me, well, its name is f, and it uses some type A that I know is a number. It takes an A and another A and results in an A. So all that I really know about those is that they're numbers. It tells me the restrictions on A back here, and then it tells me the actual signature, the actual type of F here. And we can see that if I call F of 5 and 2, I get 3 back because 5 minus 3, or 5 minus 2 is 3. Here's a slightly more interesting one. I name a function extend, and it takes some list, which I've called LST. It then takes the number 0 and combines it with that list, adds it onto that list there. Now again, it will not change the list that was passed in. It will give a new result that has some change to it. So the type of extend, we know it's taking lists, and those lists contain some type of data A. There's only one restriction on that type of data, and then it must be numbers because I've taken a number here and combined it with the existing list. So Haskell has inferred that the list will be a list of numbers. What type of numbers will they be? Integers or, a fractional or different things like that? We don't know now, but we do know they're numbers. Okay, and then I've called extend on 1, 2, 3, and it gives me 0, 1, 2, 3. I've created another function called apply, and I use it with gx, and then you see what I've done in here. What I've done is I've said gx, much like I said f52. So it's actually calling g as a function using x as input. That's what happens when you just make statements of multiple value names, is it treats them as a function call. And so essentially apply is give me some function and I'll apply it to some input that you give me. So the type of apply is it takes a function and it takes some input to that function. Notice that this type matches the input of the function, and that I will return to you the result type of that function that you gave me. So it infers all that simply from the fact that I typed gx here, because it knows that that format is a function call. Therefore, g must be a function, and x must be whatever the input type of g is, so that it can be called. Let's dig a little further into that syntax that we saw there, where we could just say gx or fx. So in an expression, fx is a function call. It's the application of the function f to the parameter x. And if I had fxy, that would be the application of the function f to the parameters x and y. So, and I can use the slightly more familiar structure of f parentheses x. It's the same thing. I could do things inside of those parentheses that would be applied before the function was called. So f parentheses x plus 1 is calling f on the result of x plus 1. We're already seeing some function composition here. If I say fx and then plus 1, that will do fx first. It will apply f to x first, and then it will do plus 1. This will lead to bad syntax for some people a lot of the time if they're trying to call a function and on the result of something else. F parentheses g parentheses x is f applied to the result of gx then, much like f was applied to the result of x plus 1. Well, here f would be applied to the result of gx here. F parentheses g space x is the same thing as f parentheses g parentheses x here, but f space g parentheses x is, confusingly enough, f called on g. So because you can apply functions to functions, we'll see plenty of examples of that later, it tries to apply f to g because function application has very high precedence. So if I want to make sure that g gets applied to x, I should put that into parentheses to override the precedence. And that goes for this version too. These both will override the precedence and cause g to be applied to x first. But if I have f space g in any way, it's going to try to apply f to the function g first. You'll often get type mismatches from these sorts of things if you weren't specifically aiming for the function f to be applied to the function g. But if you were aiming for it, you can actually get a new function by calling f on g in some cases if their types are the correct match to make that actually work. So here's some of what I was talking about before, about functions. When they take multiple parameters, they're actually sort of returning a new function. So if f has the type int to int to int, we would often read this as it having two integer parameters and giving us an integer result, like my f before that took x and y and returned the result x minus y. It had this a to a to a sort of structure, and we framed that as it takes two a parameters and returns an a parameter. But another way of thinking of it is that if it's given one int, it will return a function that takes only one more int and gives us an int result. These should be capital I, by the way. I missed that here. But so that means that if I apply f to 2, I get back a function from integers to integers. So if I called f2 for all at once, then I get an integer as a result. If I called f2 and saved that, I gave it some name, like g, if I said g equals f2, and then I said g4, I would get an integer result from that. Whatever f does to 2 and 4, it would do it. So I can apply this in many different ways. Parentheses f2 and then to 4. This creates a new function that's still going to require one integer before it returns me another integer. And so therefore its type is int because it will return an integer in the end. So we're able to give some of the parameters now and wait and give the others later. This is called currying, and we'll talk about this a lot more as we go further on. But this gives some explanation of why we see this structure of something to something to something in Haskell and in many functional programming languages. So if you want to start interacting and trying to use Haskell, the Glasgow Haskell compiler is what we'll be using in class, and it's probably the most common Haskell compiler, I believe. It's available for Unix and Windows. It has plenty of documentation around for it. We will be using version 7.10.3 as our reference. Newer versions are probably okay. There are a couple of minor differences in recent versions, but they're probably just fine for our purposes. It's available on Agate and other CS cluster machines under userbin GHC for the regular compiler, or userbin GHCI for the interactive interpreter. So you're able to just compile your programs to a compiled version that you can run at command line with GHC, or you're able to get an interactive compiler that you can type a line, see the result, try another line, etc., using GHCI. We'll sort of be able to mix some of these two, but for the most part, you can view them as two separate things. Compile your program and run it with GHC. Get something that's interpretive and interactive with GHCI. If you're a person like me who uses Emacs, there's a nice mode for it. There are probably plenty of other great plugins for your favorite IDE as well. And we will get plenty of chances to play with Haskell and learn a little bit more about the basic functionality of it here as we move forward.